chapter 10 isn't the longest chapter that we will cover this semester, far from it, but it does have quite a bit of material to keep track of, as you can see right there in the title, right? Reactions of alcohols, ethers, epoxides, amines, and sulfur-containing compounds. It's quite a bit of stuff. So make sure you keep clean, logical notes organized for the chapter. And be forewarned, it's also a direct continuation of chapter 9. Chapter 9 introduces all the ideas we're going to use in chapter 10. So if you struggled with chapter 9, make sure you're good with that foundation before we continue on to chapter 10. Chapter 9 was all alkyl halides. Now we're going to look at a lot of the same substitution and elimination reactions for the other functional groups you see in the chapter title. Looking at about 4 videos total for chapter 10. They'll all be just a little on the longer side, nothing super short, because we're dividing it into about 4 equal subsections. Okay? As we continue that discussion of group 2 from the Bruice textbook, right, where we're looking at sp3 hybridized carbons attached to some sort of electronegative group. Okay? Previously in chapter 9, it was alkyl halides, right? But we have all these other groups that are below there that are electron withdrawing as well, right? Electronegative oxygens or nitrogens or sulfurs. And the reactivity of these things depends on the specific group that's attached, as we will see in this video and for the rest of the chapter. Okay. So the first thing we're going to cover is alcohols. Okay. But look at alcohols and all the other groups that we're going to see here, okay, compared to alkyl halides. Okay? Because we know that reactivity of these things depends on the basicity of the leaving group. Okay, right? A weak base is a good leaving group. We've established that before. Okay? But alcohols and ethers, for example, are stronger bases. Okay? Thinking about the conjugate base, hydroxide or alkoxide, right? OH minus or OR minus for an alkoxide. So if it's a stronger base, that means that it's a poorer leaving group and it's less reactive. Okay. And amines, for example, are too basic, right? That NH2 minus as a leaving group, you can't really easily replace an amine. Okay. Quaternary ammonium and sulfonium, right? They have a positive charge. So those things, as we'll see in turn, are a little bit easier to react. Sulfonate esters delocalized electrons throughout this group there. So they have their own source of reactivity. Okay. Lots of things to consider, right? But let's take alcohols first, as I mentioned. That's OH minus, hydroxide is a bad leaving group. So for alcohols to react with substitutions and eliminations, they first have to be converted to have a better leaving group present. Okay. So let's see how we might do that. Okay. How do we convert that? Well, we can't do a reaction directly, right, because of that strongly basic leaving group. So we could never take bromide and just do a simple SN2 reaction and replace it there because of that strong base leaving group. Okay. We covered that in chapter 9. You can never have a better leaving group come in and replace it. Weaker base is the better leaving group, so that reaction does not proceed. But if we can take that OH and change it to an H2O, for example, now water, H2O, is a weaker base than hydroxide OH minus is. So it's weak enough to be replaced by a nucleophile. So we take the bad leaving group, OH, change it to a better leaving group, H2O, then we can replace that. Now it is a slow reaction. It's not a great leaving group and it requires heat to happen, but we can in fact do it. Okay? And traditionally here, you're only going to use things like iodide, bromide, or iodide, bromide, or chloride as weakly basic nucleophiles. Okay, to come in here and replace water. You can do it if you had an alcohol as your starting material. Your stronger nucleophiles here would end up pulling off a proton there, getting protonated in solution. Okay? But with that in mind, all of our alcohols can in fact undergo nucleophilic substitution using HBr, HI, or HCl. Okay? They just first have to be activated. Right? Activate your leaving group, then it can proceed in a reaction with a weakly basic nucleophile. So here we see HI, HBr. You can do the same thing with HCl. We'll cover that next. The difference is you do have to have heat. Okay, primary and secondary alcohols require heat. Now, tertiary alcohols do not. We'll talk about that in a second, because the mechanism depends on the structure. Okay, so primary and secondary alcohols require heat. Tertiary alcohols don't. And we go through different types of reactions. Secondary and tertiary alcohols do SN1 reactions. Let's talk about those first, right? Secondary and tertiary alcohols. We can react. Right? Notice primary and secondary heat, tertiary not. So that's one thing to consider, what requires heat. The other one is the type of mechanism. Okay, the mechanism line is drawn here. Primary do SN2 reactions. Secondary and tertiary do SN1. So let's look at those. Okay, what's going on? Here I have a tertiary alcohol. How does it react? I need to know the mechanism here from chapter 10. Yep. The first thing is my alcohol has to be activated. Otherwise it can't react, right? So the acid here, hydrobromic acid, always protonates the alcohol. It's the most basic atom in the molecule. Okay. Then I've changed my alcohol, right, to a protonated alcohol. I have a better leaving group. H2O as the leaving group instead of OH. Yep. So that allows it to act as a leaving group. Okay. It's weakly basic, so it can leave via an SN1 reaction. So it's forming the carbocation intermediate. Then the nucleophile can come back in. Okay. Now it is, in fact, a possibility that an elimination reaction occurs as well. Okay. Going straight from left to right, bromide just coming in and forming a bond, that's a substitution product. We could pull off a hydrogen off of any of those beta carbons as well, right, and form the elimination product. Okay. However, right, if you form the elimination product, that's an alkene. We know from way back in chapter 6, right, that alkene can react with HBr, and it's just going to form the substitution product because we already have HBr in solution. So that's great. That helps my synthetic yield. Okay. So this, right, going left to right, that's how you form a substituted product from an alcohol. Tertiary alcohols react faster due to the fact that they have a more stable carbocation. And it's the stability of the carbocation that allows these to react at room temperature. Tertiary don't require heat, whereas primary and secondary do. Okay? So the mechanism, if you had a secondary alcohol, would be the exact same. Okay? The difference is it would just require heat. But we couldn't do the same thing with a primary alcohol because that would mean we form a primary carbocation. Okay? So it's not going to do that. It's too unstable of a carbocation. So we must be doing these substitutions via an SN2 reaction. Okay. But other than switching from SN1 to SN2, general scheme still the same. Alcohol has to be activated, gets protonated by the acid. Yep. Then bromide acting as my nucleophile, right, comes in, boom, switches the two, we're in business. I don't have to worry about any elimination going on because bromide is too weak of a base. So if it's primary, it's SN2, requires heat. Right? If it's secondary, it's SN1, requires heat. If it's tertiary, it's SN1, does not require heat. That's what's going on with my alcohols. That's for HBr or HI. Now, HCl is a little bit different, okay, because chloride is a worser nucleophile than bromide or iodide. So actually, if we're using HCl in solution, we have to use a catalyst as well. So be on the lookout for that. If you are trying to do a substitution reaction with an alcohol and HCl, you have to use zinc chloride and heat because it's primary. Right? Zinc chloride is a Lewis acid catalyst. Right? It forms a complex, as we see here on the bottom, right, with the lone pair of electrons on oxygen. When it does that, forms this complex here, it weakens the bond between carbon and oxygen and makes a better leaving group over here. That's what allows chloride to come in, act as a nucleophile, SN2, right, kicks that whole leaving group off, and then we formed the substituted alkyl chloride in this case. So HBr, HI, nothing to worry about. If you're trying to use HCl with an alcohol, you have to use a zinc chloride catalyst as well. Okay. So make sure you have a list of all these different requirements, okay? Whether or not they require heat, whether it's SN1 or SN2, and whether they require a catalyst like this one. Okay? Another thing, of course, to keep in mind, right? We know this from chapters in the past. Secondary and tertiary alcohols are going through an SN1 reaction. That means they have a carbocation intermediate, which means, right, that should set off a flag in your brain. You need to be on the lookout for carbocation rearrangements. Okay? Because, right, specifically with secondary alcohols, we don't have to worry about it with tertiary, okay? Because the tertiary carbocation can't get any more stable. But if you have a secondary alcohol, maybe put a star in your notes there, right? Reacting with a hydrogen halide, it's going with SN1, it forms a carbocation intermediate. If that carbocation rearranges or can rearrange to form tertiary, it will. And that is where you will get your major product. So be on the lookout for that. The thing you're probably wondering right now is why is this useful, right? Why am I taking alcohols and turning them into the things I already used in chapter 9 with alkyl halides? And it just comes down to price, right? Alcohols are cheap, but they're not very reactive. Okay? It's easier to take an alkyl halide and convert it into a different type of compound. But if all you have is an alcohol to start with, then you take your alcohol, then convert it to an alkyl chloride, and then, or sorry, an alkyl halide, any one of the halogens, and then you can convert it to something else, right? Take an alcohol, convert it to an alkyl halide, then you could take it to an ether, for example, or an alkyne, right? Or put a cyanyl group right there. None of these nucleophiles would react with an alcohol. All of them will react with an alkyl halide. Okay? So that's why we're doing it. However, be aware of the fact that treatment with a hydrogen halide, right, so alcohol plus hydrogen halide, HCl, HI, HBr, is not the best method. It's not the most selective. It's also not the most productive. So the rest of this video, we have some other ways to react with our alcohols and convert them to alkyl halides. Okay. We can use an alcohol plus any one of these three solvents here to convert them to an alkyl halide. Okay. Listed in order, right? We have phosphorus tribromide, phosphorus trichloride, and thionyl chloride down here. Right, so listed left to right, they match top to bottom, the names of these reagents. Take any one of those reagents using pyridine as a solvent, and you can convert your alcohol to an alkyl halide. PBr3 will put on bromide, PCl3 will put on chloride, SOCl2 will put on chloride. That's fairly obvious here which halogen gets added, but make sure if you're using one of these, you also list on the test pyridine as a solvent. Okay? Pyridine is a basic solvent. It is involved in the mechanism as well, okay? As we can see right here. Okay? You take your alcohol, and looking at PBr3 here for starters, then we have an SN2 reaction. Okay? The lone pair on oxygen is attacking phosphorus, kicking off a bromide. That's an SN2 reaction on phosphorus. Okay? Then pyridine, which is this guy right here, comes in, right? It's a poor nucleophile, but it can come in and pull off a proton. So it's going to act as a base. That prevents your intermediate from going back. Okay. That produces a bromophosphite group. That's a good leaving group. And then the bromide that was kicked off down here comes back in, kicks off the bromophosphite group, and you get your alkyl bromide. Okay. So that's why pyridine is necessary. Same mechanism for PCl3, same mechanism for SOCl2. Right? Just make sure you know how to draw these things. Know how pyridine is important. Know that you can use any one of them to convert an alcohol to an alkyl halide. Okay. That works for primary and secondary alcohols. If you have a tertiary alcohol, right, too much steric hindrance. You can't have the backside attack that's necessary in the final step, right here, right? Chloride coming in to attack and kick off your leaving group. Can't do it for tertiary. Primary and secondary, great. Tertiary, no bueno. Okay. So what we have thus far summarized nicely right here. Alcohol, HBr, HI, HCl, right, remembering that catalyst, the 3 solvents we just talked about, including pyridine as a solvent. Okay. We can also activate alcohols and get them to react further by converting them to what's called a sulfonate ester. A sulfonate ester is right here, and that is produced by taking an alcohol and reacting it with a sulfonyl chloride. And alcohol plus sulfonyl chloride produces sulfonate ester, with, again, pyridine as a solvent. It's an SN2 reaction. Mechanism looks like this. Okay? Your alcohol attacks your sulfonyl chloride, kicks off chloride. Okay? Then again, just like we've seen before, pyridine comes in here, acts as a base, prevents your intermediate from going back. Okay? Just a simple conversion. Okay? And now I've converted, right, my alcohol with my sulfonyl chloride. They've come together to form what's known as a sulfonate ester, right? This part coming from your alcohol, the rest of it coming from your sulfonyl chloride. Those guys are useful, right, because you can control the sulfonyl chloride to control the identity over here. Okay? Then that can react further. Right? Here's a couple examples of common sulfonyl chlorides. This is a really common one. You see it known, it's referred to as tosyl chloride. You might see that abbreviation maybe on your homework, tosyl chloride. A bunch of sulfonyl chlorides. These are useful because then you have a really good leaving group. Okay, you took your alcohol, hydroxide stinks as a leaving group, but we've reacted it here with a sulfonyl chloride to form a sulfonate ester, and we have that awesome leaving group now. So any nucleophile that we introduce that's stronger than the chloride that we kicked off, right, we can now react with the sulfonate ester to form new groups via an SN2 reaction. Okay, so here's an example of 2 other nucleophiles, right? The cyano group, right here, CHS minus, strong bases, good nucleophiles. They'll come in there, attack your electrophilic carbon, you kick off that leaving group, and you can control whatever you're trying to put on the end of your carbon chain because that tosylate is so good at leaving. Again, only works for primary and secondary because tertiary alcohols would be too sterically hindered for this final step to occur when you introduce that new group. Okay, can't do the backside attack there. The other advantage here for using sulfonate esters in your synthesis is that they can react at room temperature. Okay, they don't require heat like some of our earlier reactions. Okay. Why is this such a good leaving group at the sulfonate ester? Okay. Well, if we think about electron delocalization, right, and the resonance stability, we've got this leaving group, once it gets kicked off again, that has 3 equal resonance contributors. And remember the fact that the more resonance contributors something has, the more stable it is. Okay? So that stabilization from electron delocalization means that this leaving group is now 100 times better than chloride was as a leaving group. Okay? And that's even more good. That's terrible grammar, right? But it's better than chloride and way better than an alcohol. Okay? So it's really good as a leaving group. You can introduce a variety of nucleophiles this way, taking an alcohol plus a sulfonyl chloride to form a sulfonate ester. Then any nucleophile you add in, pretty much you're guaranteed to be able to introduce it onto that carbon chain. Okay. One thing to be on the lookout for, right, is the mechanism when you're thinking about stereochemistry for your final products. Because if you are doing a reaction with phosphorus tribromide or phosphorus trichloride or thionyl chloride, that SOCl2, right, any of those guys, right, the configuration of your final product is the same as the configuration of the alcohol that you began with, right? So if you were R to start, you're R to finish, or if you were S to start, you're S to finish. Okay, but if you're using a thionyl chloride, the configuration that you end up with is opposite. So if you were R to start, you're finishing S, or S to start, you're finishing R. And that's because of the way the reactions happen, okay? If you're doing the PBr, the PCl3, or the SOCl2, it's two SN2 reactions, okay? So you go, let's say, we go from, we're starting with R, okay? Well, we activate our leaving group, so we were R, we're still R, right? Then we bring in bromide, R to S, and then when we do a new nucleophile, then we're back to R, okay? So R to S to R. So two SN2 reactions, meaning you end up with the final configuration that you started with. Okay? Not that it stays the way, it just ends up where you started. Whereas with a thionyl a sulfonyl chloride, okay, tosyl chloride, for example, in pyridine, that last reaction we talked about, that just uses one SN2 reaction. Okay, so if you were R, you finish S. If you were S, you finish R. One more thing to add in your notes when you're summarizing all these reactions. It's a lot to start with. Okay, in this video too, probably have the most introduced in all of them. This is just substitution reactions of alcohols. We're going to talk about eliminations in the next video, but make sure you've got all of those things listed for exactly what's going on. There's that table that's somewhere in your notes there. Right? This one plus the final reaction we talked about will summarize all the different substitution reactions of alcohols.